The hobbyist deploys resources. The architect governs infrastructure. That's the line. That's where it splits. Most Bicep files you see are just click next translated to code. Someone took a portal workflow, wrote it in syntax form, and called it infrastructure as code. But it's not. It's automation, not architecture. Enterprise Bicep is different. It's about lifecycle, ownership, and predictability. 3 separating principles drive the difference. Scope above subscriptions, contracts enforced in code, and state managed as a first-class concern. What you're actually building isn't a template. It's a blueprint that survives organizational change. It's the thing that remains true when people leave, when teams restructure, when business priorities shift. That's the architecture question we're answering today. Why Bicep isn't just ARM with better syntax. ARM templates are powerful. They're also verbose, dense JSON, nested quotation marks, escape characters, long property names repeated across every resource definition. Bicep strips that ceremony, shorter syntax, better readability, modules, parameters with constraints, variables. All of that makes Bicep easier to write, easier to maintain, easier to share with teams. But here's where most conversations about Bicep stop, and here's where they get it wrong. Microsoft isn't positioning Bicep as better ARM syntax because they want prettier JSON. That's not the strategy. The real shift is this. Bicep is now the vehicle for infrastructure as policy. Deployment stacks introduce state awareness. You're no longer just tracking deployment history, you're tracking resource ownership. You're managing lifecycle. When a resource disappears from your template, the system knows what to do. Delete it, detach it, or leave it alone. That's not syntax improvement. That's a fundamental change in how infrastructure relates to governance. Management group scope used to be optional. Nice to have for large organizations. Now it's foundational. You deploy policy definitions at the management group level. You assign initiatives to hierarchies of subscriptions. You codify role-based access control. You're not just deploying resources anymore. You're defining organizational control planes. Azure verified modules standardize what a good module looks like, and they do this across both Bicep and Terraform. This matters because it means your architectural standards aren't locked to one language. You're building a governance model that can move between tools without changing its shape. The implication is significant. Infrastructure code is no longer optional. It's the control plane itself. This changes how you think about modules. A module isn't just a reusable template anymore. It's a contract. It encodes organizational decisions, security baselines, naming conventions, compliance requirements. Everything your organization decided matters about how infrastructure should look. That's in the code now. It changes how you think about scope. You're not choosing between resource group, subscription, and management group based on convenience. You're choosing based on governance boundaries. Does this policy apply to one team or to the entire organization? That answer determines your scope. It changes how you think about lifecycle. Bicep deployments used to be fire and forget. Deploy the template, get the resources, move on. Now you're managing the full lifecycle of those resources as a unit. Updates, teardowns, ownership tracking, all of it coordinated through code. The distinction matters because it reshapes everything downstream. Your module design, your parameter strategy, your access controls, your CI/CD pipeline, your organizational structure around who approves what. Understanding this distinction requires looking at what actually changed in the Azure platform. And that's where we're going next. The new model, what changed in 2026? Here's the inflection point. This is where abstract architecture becomes concrete practice. In July 2026, Azure Blueprints are gone. That's not a soft deprecation. That's the end of a service. Blueprints were Microsoft's attempt at a unified governance and deployment model. They bundled templates, policies, and role assignments into a single artifact. But they had limitations. They couldn't manage resource lifecycle cleanly. They didn't track ownership at scale. They didn't integrate deeply enough with the organizational hierarchy of management groups. Deployment stacks are the successor. And they're not just a replacement. They're a rethinking of what it means to own infrastructure. Before stacks, your Bicep deployment was a one-time event. You ran the template, resources got created, Azure forgot about the relationship. If you modified the template 3 months later and redeployed, Azure didn't know which resources belonged to this deployment and which were orphaned. You had to manage that yourself. Stacks changed the model. A stack is an Azure resource. Microsoft. Resources deployment stacks that wraps your Bicep template and maintains a persistent record of what it owns. When you update a stack, Azure compares the new template to the old one. It knows which resources are new, it knows which have been removed, and it knows exactly what to do about it. Delete them, detach them, or leave them alone. That's a state model. It's how Terraform has always worked. Now it's native to Azure. This matters operationally. It means environment lifecycle becomes predictable. Spin up a dev environment in the morning, tear it down at night, completely, automatically, without worrying about orphaned resources or cascading failures. In a brownfield migration, you can gradually move resources under stack management without breaking production. In a production update, you can remove a resource from your template and be confident it will be cleaned up in a controlled, auditable way. Management group scope, which we touched on earlier, is now the entry point for everything that touches organizational control. You're not just deploying resources at the management group level. You're codifying policy. You're assigning roles. You're saying, this is how governance works in our organization, and it lives in code. Azure verified modules have evolved too. They're not just Bicep modules anymore. They're a shared specification that applies to both Bicep and Terraform. Same naming, same parameter structure, same security defaults, same testing requirements. This convergence is deliberate. It means you're not building an architecture locked to one language. You're building standards that can survive technology transitions. The implication sinks deeper than it first appears. Infrastructure code isn't an alternative to clicking the portal anymore. It's not a faster deployment option. It's become the control plane itself. This shifts into three concrete changes that separate the 2026 model from what came before. First, lifecycle management. Resources are no longer fire and forget. They have ownership tracked in code. They have defined behavior when they're no longer needed. Second, contract enforcement. Modules don't just encapsulate resources, they encapsulate organizational decisions, security baselines, naming standards, compliance requirements, all of it baked into the code as constraints, not suggestions. Third, governance as code. Policies don't live in an external system, they live in your Bicep definitions. Role assignments are versioned in Git. Policy initiatives cascade through management group hierarchies defined in code. Governance is infrastructure now. These aren't incremental improvements, they're architectural shifts, and understanding them requires grounding this in the actual decisions you have to make when you start building. The scope problem. Why subscriptions aren't enough. Okay, so here's the first decision you make when you write a Bicep file. Where does this code live? What scope are you targeting? Most organizations start at resource group scope. It's the natural place. You've got a resource group, you want to deploy some storage accounts, some networks, some compute into that group. The scope is clear. The boundaries are obvious. The blast radius is contained. A broken template messes up one team's resources, not the whole organization. It feels safe. And for small projects, it is safe. But watch what happens as you scale. You're not deploying to one resource group anymore. You're deploying to 10, then 50, then 100. You've got environments, dev, test, staging, production, each one with its own resource group. Then you've got regional variants, US resources, EU resources. Then you've got teams, platform team, application teams, security teams, each managing their own collections of resource groups. Now ask a simple question. Who owns that subscription? Not who has contributor access. Who actually owns it? Who makes decisions about it? Who updates the billing account if the credit card expires? Who says yes or no to a new policy? And who decides if the subscription gets decommissioned? In small organizations, that's easy to answer. In medium organizations, it's getting fuzzy. In large enterprises, it's chaos. You've got subscriptions that no one person can fully describe. They've accumulated resources over years, policies that were added, never removed, role assignments that predate half the current team. Someone left, but their service principle is still being used. And here's the architectural problem. Subscription scope is where the real governance questions live, not the does this template have the right network configuration questions, the who decides what policies apply to this entire cloud footprint questions. That's where management group scope enters the picture. Management groups sit above subscriptions. They're a tier of the hierarchy you don't typically see unless you're thinking architecturally about how your cloud is organized. And the key difference is this: policies assigned at a management group cascade down to every subscription beneath it. Every single one. Role assignments propagate. Baselines get inherited. You define something once at the management group level and it applies to hundreds of subscriptions automatically. That's where governance lives. When you write Bicep at management group scope, you're not deploying resources anymore. You're defining the rules that govern how resources can be deployed. You're saying every subscription under this management group must enforce TLS 1.2 for all storage accounts. You're saying every resource group must have these 3 tags. You're saying only these service principals can assign roles in these subscriptions. And here's where the architecture question becomes real. Are you building infrastructure, or are you building the governance model that infrastructure happens to implement? Because those are different conversations, different skills, different approval processes, different stakeholders. The first decision point is Bicep's target scope parameter. That one line, target scope equal management group, determines whether you're thinking about serving one team's deployment needs or defining organizational control. It's not a technical detail, it's an architectural statement. Moving to management group scope doesn't just change what you can deploy, it changes how you think. You're suddenly managing inheritance. If you modify a policy at the platform management group level, what happens to the 3 child management groups beneath it? If you assign a role at the management group level, who inherits it? What happens when someone adds a new subscription? Does it automatically get the baseline, or do you have to manually onboard it? Those aren't rhetorical questions. Those are the questions that determine whether your infrastructure survives organizational change or becomes a liability. This scope decision directly affects how you structure your modules. Parameters and variables. The contract layer. Parameters are your interface to the outside world. They're how someone using your template says what they want. But that's only half the story. In a hobby project, you might write a parameter like param location string. Simple, open-ended. Whoever calls your template can put anything there. That flexibility feels good at first. You're not forcing constraints. You're trusting the user to know what they're doing. Enterprise Bicep flips that assumption. You stop trusting flexibility. You start enforcing intent. A parameter in production Bicep isn't just an input variable. It's a guardrail. It's the organizational rule embedded directly in the code. When you write param location string in an enterprise template, you're not actually being flexible. You're being negligent. You're saying, we don't care if someone deploys to Kazakhstan because they mistyped the region name. We'll find out later. Instead, you use decorators. Add aloud Eastus, Westus, North Europe. Now the parameter is a contract. It says, these are the regions we support. Nothing else gets deployed. Not because we're being restrictive. Because that's the actual organizational boundary. You've got data residency requirements. You've got network backbone in specific regions. You've got cost controls based on region. Those aren't technical details. Those are business rules. At min length 3 and at max length 24 aren't style guides. They're enforcement. A storage account name has hard limits in Azure, but your organization might have additional constraints. Maybe all storage account names must follow a specific pattern. Maybe they must start with your company prefix. The decorator layer is where that business logic lives. At descriptions looks cosmetic. It's not. It's documentation that surfaces in tooling, in parameter files, in IDE hints. When someone's writing a Bicep file and they hover over your parameter, they don't just see the type, they see the meaning. This is the cost center that will be billed for this resource. That's context. That's what prevents mistakes. Variables do something different. They encode consistency. A parameter might say, what are the tags for this resource? A variable says, if you didn't provide tags, here are the defaults, and here's the logic that applies organizational standards to whatever you did provide. A parameter might say, what's the environment name? A variable might apply that to determine the network range, the backup retention period, the monitoring verbosity. The parameter is the input. The variable is the business logic that translates that input into reality. The distinction matters. Hobby projects use parameters for flexibility. Enterprise projects use parameters to prevent mistakes and variables to enforce consistency. User-defined types let you push this further. You can create a type that represents a compliant storage account. That type encapsulates every decision about what makes a storage account compliant in your organization. Every time someone uses that type, they're inheriting all those decisions without having to reinvent them. Parameters and variables are where you move from the template that builds our infrastructure to the template that enforces our organizational standards. This enforcement is foundational because modules, the next layer up, are built on top of it. Modules as organizational standards. Now we get to the level where all of this comes together. Parameters and variables are the foundational layer. Scope decisions determine where governance lives, but modules are where the entire architectural vision crystallizes into something teams actually use. A module isn't just a reusable template. That's a technical description. A module is a contract. It says, this is how we do networking in our organization. This is how we do identity. This is how we do compliance. When someone consumes your module, they're not just getting a block of Bicep code. They're inheriting organizational decision-making. Here's the practical reality. Azure Verified Modules, AVM, provides the baseline. Microsoft has done the work to understand what a production-ready networking module looks like, what a compliant storage account needs, what a secure AKS cluster requires. You don't start from nothing. You inherit Microsoft's architectural thinking, but, and this is critical, your organization's modules wrap AVM and add your rules. You don't just publish Microsoft's AVM module, you create an internal wrapper. That wrapper might enforce your naming convention. It might require your cost center tags. It might add your security baselines on top of Microsoft's defaults. It might constrain parameters to your approved SKUs. The wrapper becomes your organizational standard. Teams don't consume AVM directly. They consume your module, which happens to use AVM as its foundation. This is where the 70-30 split becomes visible. 70% of what a module does is strategic. It encodes business decisions. What naming pattern do we use? What security controls matter to us? What monitoring is mandatory? What cost controls apply? 30% is technical, the actual Bicep syntax that implements those decisions. When you design a module, you're not sitting in a technical meeting deciding how ARM templates work. You're sitting in an architecture meeting deciding how your organization works. There are 3 types of modules in the mature model. Understanding the distinction changes how you organize your entire module strategy. Resource modules wrap a single Azure resource. A storage account, a virtual network, a key vault, but they wrap it with organizational guardrails already baked in. You can't create a storage account through the module without encryption enabled. You can't deploy a network without the required network security groups configured. The module takes complexity off the table. Pattern modules orchestrate multiple resources into a recognized architecture. A hub-spoke network pattern, a landing zone for a workload, a secure AKS cluster with all its prerequisites. These modules are where architectural decisions become reusable. You're not just standardizing individual resources, you're standardizing how those resources fit together. Platform modules are the broadest layer. These are the entire subscriptions as a service blueprints. Everything needed to hand a team a fully configured environment. Networking, identity integration, baseline policies, monitoring stacks, security controls, all as one coherent unit. The architectural hierarchy matters because it mirrors how your organization actually works. A platform team defines platform modules. Teams build pattern modules on top of them. Application teams use resource modules to fill in specifics. Different governance applies at each layer. Versioning becomes critical here, and this isn't theoretical. A resource module has a breaking change. Maybe you removed a deprecated parameter. Maybe you changed the output structure. If 30 teams depend on that module and you deploy that breaking change, 30 teams suddenly have broken templates. This isn't a compilation error they catch at test time. This is production breakage. This is why module versioning isn't optional. It's a hard requirement. Semantic versioning, clear deprecation paths, migration guides. The governance question becomes operational. Who can publish modules? In some organizations, anyone can. In most mature ones, no. The platform team publishes. Application teams request new modules or modifications. Reviews happen. Testing happens. Once it's released, it's stable. It won't break without explicit version bumping. Who reviews them before publication? Usually cross-functional. Does it meet security standards? Does it follow naming conventions? Does it align with organizational cost controls? Does it integrate with the monitoring baseline? How do you enforce their use? That's where policy comes in. You might prevent teams from deploying certain resources directly. They must use the module. You might audit which modules are being used across the organization. You might deprecate old modules by refusing to renew their support. Modules become the unit of organizational control. This multiplies the architecture problem across every team and every deployment. Outputs and dependencies. The invisible architecture. Outputs might be the most underestimated part of Bicep architecture. When you're writing a module, outputs feel like afterthought work. You extract the resource ID of what you just created. You throw it in an output block. Done. That's not architecture, that's plumbing. In reality, outputs define the interface between layers of your infrastructure. They're not values you extract. They're promises about what downstream systems can rely on. Picture this. You've got a networking module. It creates a virtual network, subnets, network security groups, route tables. At the end, it outputs the subnet ID. That subnet ID gets consumed by an application module. That application module deploys VMs into that subnet. The dependency relationship between those two modules, the fact that one produces what the other consumes, that's your architecture. It's not written down in a diagram. It lives in the outputs and the parameters that consume them. Now, scale that across an enterprise. You've got dozens of modules, hundreds of deployments. The networking team publishes a new version of their module. They optimize the subnet ID format, or they change how subnets are named, or they add a new output that more accurately represents what's actually available. That change cascades through every application module that depends on that output. It cascades through every team's pipeline. It cascades through every deployment. This is where Enterprise Bicep runs into complexity that hobby projects never see. In a small environment, you've got maybe 5 modules in total. You can track the dependencies in your head. In a large organization, you've got hundreds. The dependency graph becomes invisible. A change in one place breaks things in 10 others. Teams don't even know the connection exists until production starts failing. Here's the architectural problem. Bicep doesn't have a built-in dependency resolver. There's no system that says if this output changes, warn all consumers. You have to manage it manually, through parameter files, through orchestration logic, through careful naming conventions and documentation, through discipline. This is why outputs need to be minimal and intentional. Every output you expose is a surface that others will build on. Every output is a contract. When you add an output, you're making a promise. Downstream modules can rely on this. If you remove it, you break that promise. If you change its format, you break that promise. The smaller your output surface, the fewer promises you make. The fewer promises, the more flexibility you have to change your module without cascading failures. The architectural question becomes this: are your outputs enabling flexibility, or are they creating hidden coupling? A poorly designed output exposes internal implementation details. Here's the exact resource ID, formatted like this, named exactly this way. Now, downstream modules are coupled to those specifics. If you change the naming, everything breaks. If you refactor internally, everything breaks. A well-designed output provides a semantic contract. Here's what you need to access the network capability this module provides. The implementation might change. The output stays stable. That's the difference between outputs that enable architecture and outputs that create scaffolding you're locked into. Managing these dependencies at scale requires a completely different approach to how you orchestrate deployments. Deployment stacks, the state management breakthrough. For years, Bicep had a structural gap that Terraform didn't. You could deploy resources. Azure would create them. And then, the relationship ended. You'd run a Bicep template. Resources appeared in Azure. Weeks later, you'd modify the template, remove a resource, redeploy, and Azure wouldn't know. It wouldn't track which resources belonged to that deployment. It wouldn't know if the removed resource should disappear or stick around. You'd have to manage that yourself, delete it manually, or leave it orphaned, or write scripts that try to guess. This is why brownfield environments get messy. Years of deployments stack on top of each other. Nobody knows which resources are safe to delete and which are supporting some critical workflow that nobody documents. Terraform solved this with state. A.tf state file that said, I created these resources. These are my responsibility. If they're no longer in my configuration, they should be cleaned up. State made infrastructure predictable, but state came with operational cost. You had to store it securely, lock it during updates, back it up, manage its lifecycle like production data, because it was. Deployment stacks bring Terraform's model into Azure natively. No separate state file, no external storage complexity, but the same fundamental capability, ownership tracking. A deployment stack is an Azure resource. Not a file, not a concept, an actual resource of type Microsoft. Resources deployment stacks that sits in Azure and owns a collection of other resources. When you create a stack, it wraps your Bicep template. Every time you deploy, the stack maintains a manifest of what it owns. New resources get added to the manifest, changed resources get updated. Removed resources get handled according to your settings. And here's where the lifecycle options become critical. Delete resources is the aggressive option. You remove a resource from your Bicep template, redeploy the stack, and Azure deletes that resource. Completely, automatically. This is powerful for dev and test environments. Spin up a dev stack in the morning, delete it at night, everything disappears. No orphaned resources, no stray databases still accruing charges because nobody remembered to clean them up. But delete resources in production is a different conversation. You remove a resource by accident, code gets merged, pipeline runs, your database is gone. That's not governance, that's catastrophe. So the safer production approach is detach all. You remove the resource from the template, the stack stops managing it, but the resource stays in Azure. You can delete it manually, or migrate it to another stack, or hand it off to someone else who owns it. The stack is saying, I no longer own this. What happens to it is someone else's decision. There's also detach resources, which is surgical. You specify exactly which resources get detached. Everything else follows the delete behavior. This matters for complex migrations where you're gradually moving resources under stack management. Some resources stay with the stack, others get handed off. Deny settings are the governance layer on top of lifecycle management. By default, once a stack owns a resource, anyone with contributor access can still manually modify that resource in the portal. That breaks the code is truth principle. Deny settings fix this. When you enable deny, write, and delete on a stack, Azure prevents modifications to stack-owned resources outside the ISE workflow. The portal buttons don't work. CLI commands are blocked. Even if you have the permissions, you can't change those resources. The only way to modify them is through the stack, which means through the Bicep template, through the pipeline, through code review and approval. This is where discipline becomes architectural. You're not trusting teams to follow a process. The system enforces the process. Configuration drift becomes technically impossible, not just discouraged. Stacks work at resource group, subscription, and management group scopes. This is significant. A stack at subscription scope can own resources across multiple resource groups. You're not confined to single resource group deployments anymore. You can deploy an entire subscription as a coherent unit. Every resource, every policy, every role assignment managed by one stack. Update the stack template, the entire subscription converges to the new state. This changes environment management fundamentally. Development environments become temporary, provisioned on demand, deleted completely at the end of the day. Production environments become versioned. The stack template lives in Git. Every change is traced. Rollback is just deploying an older template version. The implication is this: you can finally implement true environment lifecycle management in Azure natively. Spin up, update, tear down, all predictably, all auditable, all under code control. This is the foundation for governance at scale. Management group scope, governance at the tenant level. You've moved past resource group thinking. You've accepted that scope matters architecturally. Now you're standing at the level where organizational governance actually lives. Management groups sit above subscriptions in the Azure hierarchy. They're the tier most teams never interact with directly unless they're in a platform or governance role. But that invisibility is the point. Management groups are where policy cascades, where role assignments propagate, where a single decision made at the right level applies to hundreds of subscriptions automatically. When you deploy Bicep with target scope equals management group, you're no longer defining resources. You're defining the rules that govern how resources can exist in your organization. Think about what that means operationally. You write a policy definition. You assign it at a management group scope. Every subscription beneath that group, whether there are 10 or 200, inherits that policy. Every resource created in every one of those subscriptions gets evaluated against that policy. You didn't deploy that policy to 200 subscriptions. You deployed it once, the hierarchy did the work. The typical organizational structure looks like this. Tenant root sits at the very top. Beneath it, you've got a platform management group. This is where central infrastructure lives, where shared services, connectivity standards, and security baselines are defined. Beneath platform, you've got landing zones. This is the actual structure where application teams sit. And beneath landing zones, you've got individual subscriptions, production subscriptions, non-production subscriptions, sandbox subscriptions, each one inheriting governance from the level above. What you're deploying at management group scope are primarily three resource types. Policy definitions, the actual rules, policy initiatives, bundles of multiple policies that work together as a coherent governance model, and RBAC assignments, role assignments that determine who can do what at what scope. You're also deploying things like diagnostic settings that push logs to centralized monitoring, and custom role definitions that your organization needs. The architectural shift here is that governance is no longer something you do after infrastructure is built. It's not a separate process. It's part of the infrastructure definition. You're not building a resource group, then separately deciding what policies apply to it. You're defining a management group with specific policies already embedded. That management group becomes a container that enforces governance on everything created within it. This requires elevated permissions. You can't deploy to management group scope from a standard developer account. This is intentional. It's a forcing function. Governance changes aren't something casual. They're deliberate, they're auditable, they go through approval processes. Someone signs off on the fact that we're changing how the entire organization's cloud infrastructure behaves. Here's where this becomes real. When a new subscription gets created and placed under a management group you've configured, it doesn't need individual setup. It doesn't need a team to manually apply policies. It inherits everything. The policies, the role assignments, the monitoring baselines, the compliance checks. The governance is already there. The subscription is already compliant by definition. That's not a deployment convenience. That's a change in how you think about onboarding. It also changes what maintenance means. If the security team decides that all storage accounts need a new encryption requirement, they don't update hundreds of policies individually. They update the policy definition once. The change propagates down. Every subscription sees it. Every resource gets reevaluated. Compliance reports update automatically. One change. Organizational scale. But this only works if governance is truly codified, if it lives in Bicep, if it's versioned in Git, if it goes through the same review and approval process as application code. If it's not, you're back to manual processes at organizational scale. That's the opposite of what you're trying to achieve. This is why management group scope isn't optional for enterprise Bicep. It's foundational. Azure policy as code, enforcement through Bicep. Now you have the structure. Management group hierarchies, scopes defined, the governance model sitting at the tenant level, but structure is just the skeleton. The actual enforcement, the part that stops bad things from happening, that's Azure policy. Azure policy is the mechanism. Bicep is how you define it. This is a crucial distinction. You can write policies in the portal, click through a UI, build rules visually. Many organizations do exactly that. But that's not architecture. That's configuration that nobody can review, track, or reproduce. Enterprise governance lives in code. Policy definitions are the fundamental unit. They're the actual rules. A policy definition might say, all storage accounts must have encryption enabled. Another might say, only these 3 Azure regions are allowed for resource deployment. Another, every resource must have a cost center tag. These are constraints. They're written as JSON rules, and they can be deployed via Bicep as Microsoft. Authorization/policy definitions resources. You've got 2 sources for these definitions. Custom definitions, rules your organization writes because they matter to your business, and built-in definitions, Microsoft's rules for security, compliance, and best practice. Both deploy the same way. Both get assigned the same way. But the distinction matters. Built-in policies get updated by Microsoft. Custom policies are your responsibility to maintain. The next layer is initiatives. An initiative, also called a policy set definition, bundles multiple policies together into a coherent governance model. A security baseline initiative might include 20 individual policies, encryption requirements, authentication standards, logging rules, access controls, all the pieces that together define what security looks like in your organization. Instead of assigning policies individually, you assign the initiative. One action, 20 policies applied. Assignments are where the work actually happens. A policy definition is a rule. An assignment is that rule applied to a scope. You might assign a baseline initiative at your platform management group. Now, every subscription beneath that group inherits the policy. Every resource created gets evaluated, compliant or non-compliant. That evaluation doesn't require a manual review. It's automatic, continuous, built into the platform. Now, here's where the architecture gets interesting. Policy has an effect called deploy if not exists. This isn't just evaluation. This is enforcement by deployment. The policy doesn't just check if your storage account has encryption. It can actually deploy an encryption configuration if it's missing. That's powerful. It's also constrained in ways that matter architecturally. The constraint is scope. Deploy, if not exists, works at subscription scope, at resource group scope, but not at management group scope. You can't write a policy that automatically deploys something to the management group itself. This is a technical limitation that shapes how you distribute governance across your infrastructure. This limitation drives a pattern that separates concerns cleanly. Use Bicep deployments at management group scope for the governance artifacts themselves. Policy definitions, initiatives, role assignments. These are the rules and the access controls. Then use policy assignments, also deployed via Bicep, to apply those rules. For anything that needs to deploy to a subscription or resource group, maybe a compliance module, maybe a monitoring agent, use deploy if not exists policies. Let the policy engine handle the deployment to the subscription level. The result is clean separation. Bicep handles the structural governance at the management group level. policy handles the continuous enforcement at the subscription and resource level. Together, they create a governance model that's declarative, auditable, and continuously enforced. This is where policy transitions from something the security team configures to something embedded in your organizational architecture. RBAC and identity as code. Role assignments are infrastructure. This is a statement that shifts how you think about access control. Not role assignments are managed by the security team. Not role assignments are configured in the portal. Role assignments are infrastructure. They should sit in Bicep files. They should be versioned in Git. They should move through the same pipeline, validation, testing, approval, that any other infrastructure change moves through. Because access is foundational. Everything we've discussed up to this point, policies, modules, scopes, none of it matters if the people implementing it don't have the permissions to do so. And conversely, if people have access they shouldn't have, all the policies in the world won't prevent problems. Access control isn't a separate concern, it's infrastructure. The principle guiding this is least privilege. You assign exactly the permissions needed, at exactly the scope needed, to exactly the identity that needs them. Not a role higher than required, not a scope broader than necessary, not to an identity that doesn't actually need it. This sounds simple. In practice, it's the discipline that separates secure organizations from everyone else. There are 3 primary identity types you assign roles to, and understanding the distinction changes your architecture. Service principals are identities you create and manage. They have credentials, passwords, or certificates. You're responsible for their lifecycle, their rotation, their security. This is operational overhead. It's also why Terraform and other tools need to store credentials to authenticate to Azure. Managed identities eliminate this category of operational burden. An Azure resource, a VM, a function app, a container, gets a managed identity automatically. Azure manages the credentials. There's nothing to rotate, nothing to store in a vault. The resource can authenticate to Azure services using its identity. This is increasingly the preferred approach because it removes an entire class of operational problems. Azure AD groups, now Entra ID groups, are the third category. These are organizational identities. A group called Platform Team contains people. That group gets assigned a role. Now everyone in the group has that permission. When someone joins the team, they get added to the group. They automatically inherit the role. When they leave, they're removed. The role assignment doesn't change. You're managing team membership, not individual role assignments. The architecture question that surfaces here is this: who can assign roles? And more specifically, who can assign roles that control who assigns roles? This is where RBAC becomes recursive. You need role assignments to govern role assignments. At the top, someone has owner at the tenant root. That's a hard starting point. Someone has to have ultimate permissions somewhere. But from there, you can delegate. The owner assigns owner to a platform team at the platform management group. The platform team can now assign roles to others at that scope and below, but not above. This creates a hierarchy of control. A ladder of delegation that mirrors organizational authority. When you codify this in Bicep, you're making those delegation decisions explicit and auditable. A Bicep file at management group, scope that assigns roles to the platform team. That's a policy decision, documented in code, reviewable in a pull request, traceable in audit logs. If someone later asks, why does the platform team have these permissions? You have a Git history explaining when and why the decision was made. Managed identities shift this dynamic further. A Bicep file can create a managed identity, assign it specific roles at specific scopes, and embed it directly in the infrastructure definition. Now the application has exactly the permissions it needs. No more, no less. The application isn't running with an overprivileged service principal, it's running with an identity purpose built for its needs. Identity governance only works at scale if it's codified. If it's infrastructure, Azure Verified Modules, AVM, the standardization framework. Up to this point, we've been building the architecture, scopes, parameters, modules, deployment stacks. But there's a critical question that hasn't been answered. Where do these modules come from? Does every organization start from scratch and build their own, or is there a foundation to build on? AVM is Microsoft's answer, and it changes the conversation fundamentally. AVM stands for Azure Verified Modules. It's not a tool, it's not a service, it's a specification, a formal definition of what a production-ready module looks like across both Bicep and Terraform. This convergence is significant. It means your architectural standards don't have to choose a language. They can live above the implementation details. Here's why that matters. Organizations traditionally faced a choice. Build your modules in Terraform because you're multi-cloud. Build your modules in Bicep because you're Azure native. Either way, you're building from first principles. You're deciding what parameters look like, how outputs are structured, what security defaults are non-negotiable. You're reinventing the wheel. Different teams in the same organization build modules differently because there's no shared standard for what different means. AVM changes this. Microsoft has already done the thinking. They've looked at what a production storage account needs. They've looked at what a secure virtual network requires. They've looked at what a compliant AKS cluster looks like. They've encoded all of that into modules. And this is the part that matters. They've done it in both Bicep and Terraform simultaneously, following the same specification. The resource modules are the foundational layer. These wrap single resources, a storage account, a virtual network, an app service plan, but they wrap them with security defaults already applied. You can't create a storage account through the AVM resource module without encryption enabled. You can't deploy a network without the required network security groups. The module has already made the hard decisions. Your job isn't to decide if encryption matters. Your job is to choose where the data lives. Pattern modules go a layer higher. These orchestrate multiple resources into recognized architectures, a hub-spoke network, a landing zone, a secure Kubernetes cluster with all its prerequisites. These modules aren't designed to be universally applicable. They're designed to be foundational. You don't use them unchanged. You use them as starting points. You customize them, you extend them, but you're not inventing the pattern, you're inheriting it. AVM also specifies the contract layer, how parameters are named, what outputs are guaranteed, what documentation is required, what testing standards apply. This standardization matters because it means a module built by Microsoft follows the same conventions as a module built by your platform team. They fit together. They can be composed. They don't create a Tower of Babel where every module has a different interface. The implication is profound. You don't start from nothing. You inherit Microsoft's architectural thinking and customize it for your organization. This isn't about taking shortcuts. It's about not starting at the bottom of a mountain that's already been climbed. Microsoft has spent years understanding how Azure resources should be configured securely, resiliently, and operationally. That work exists. You can use it. You can build on it. You can modify it, but you're not rediscovering it. Versioning and maintenance reinforce this. AVM modules are versioned, semantic versioning, clear release notes, deprecation paths. When Azure releases a new feature, Microsoft updates the module. When a security vulnerability is discovered, it gets patched. When a best practice changes, the module gets updated. You don't maintain the module, you consume it. You update it when Microsoft updates it. The organization publishing the module is responsible for keeping it current. This is where standardization leaves the realm of theory and becomes operational. You're not trying to convince teams that they should follow standards. The standards are already built into the modules they're consuming. Compliance isn't something they opt into. It's the default behavior of the tool they're using. This foundation, AVM, is what makes building your organization's modules actually feasible. You're not creating 70 resource modules from scratch. You're wrapping AVM modules. You're adding your naming standards, your cost center requirements, your monitoring baselines. You're customizing, not inventing. That's when your modules become truly organizational. Building your first module, the pattern, so you understand the architecture. You know why modules matter. You've got AVM as a baseline. Now you're sitting down to actually write one. What does a production module look like? There's a structure. It's not arbitrary. It's shaped by the needs of scale. Start with the file layout. Your module has a main file, main, Bicep. This is where the actual resource definitions live. Before that, at the top of the file, you declare your parameters. These are the inputs, the questions you're asking anyone who uses this module. What's the location? What's the environment? What's the resource name? What SKU do you want? These parameter declarations come first because they establish the contract immediately. Someone opening your module sees the parameters and knows what decisions they need to make. Parameters aren't loose. You use decorators. At min length 3, because Azure requires it. At max length 24, because Azure limits it. At allowed dev and test or prod, because your organization only runs these 3 environments. These constraints aren't restrictions, they're clarity. They're saying, here's what's actually valid. Here's what makes sense given our organizational constraints. Next come variables. Variables are where the module thinks. If a parameter says environment, a variable translates that into actual decisions. If the environment is prod, the variable sets the SKU to premium. If it's dev, standard. If it's prod, backups run daily. If it's dev, weekly. The variable is where business logic lives. It's where you say, given these inputs, here's what actually matters. Then resources. These are the actual Azure objects. But notice, they're parameterized. The resource name uses parameters. The location uses parameters. The tags use variables that consumed parameters. The same module file works in dev and prod. The only difference is the parameter file. The Bicep stays the same. This is where portability lives. Outputs come at the end. But here's the discipline. Minimize them. Every output you expose is a promise. It's saying downstream modules can rely on this. If you remove it later, you break downstream code. The tighter your outputs, the more freedom you have to refactor the module without breaking consumers. Output the resource ID if it's needed. Output important properties if they're genuinely necessary. Don't output everything. Expose only what's architecturally necessary. Documentation is not optional. It's part of the module. Every production module has a README. This isn't a formality. It's operational necessity. The README explains what this module does, what problem it solves, what parameters mean, what outputs you get, what assumptions it makes about your environment. If your organization requires cost center tags, the README says that. If the module only works on certain Azure regions, the README lists them. If there are security implications, the README explains them. Someone new to your team picks up a module. They read the README. They understand what it does. They understand what it costs. They understand what it requires. They don't have to guess. They don't have to reverse engineer. Testing is a discipline that's often skipped. Don't. Bicep validate catches syntax errors. Run it. What if deployments show you what will actually be created before you create it? Run them in a test subscription. Policy compliance checks validate that whatever you deploy will pass your organizational policies. Run them. If your module creates a storage account that would fail your encryption policy, you want to know in validation, not in production. A production module is structured, documented, tested. It's not a one-time script. It's infrastructure that other teams will build on. It's infrastructure that your organization will rely on for years. That structure is where theoretical architecture becomes practical reality. Module, registries, and governance. Modules need to live somewhere. This sounds obvious until you're standing in an organization with 50 modules scattered across 5 different Git repositories, 3 owned by the platform team, 2 owned by application teams, none versioned consistently, half of them duplicating the work of the other half. Azure Container Registry is the standard for Bicep modules. This isn't a technical requirement. You could host Bicep files anywhere. But ACR becomes the mechanism for centralizing, versioning, and controlling access to your module library. It's not just storage, it's governance infrastructure. When teams publish modules to ACR, they're publishing to an internal marketplace. This isn't marketing language, it's operational reality. Teams need to discover modules. They need to know what exists. They need to know what's safe to use. They need to know if a module is actively maintained or deprecated. A registry becomes the interface through which your organization communicates about infrastructure standards. Someone on an application team is building a new resource group. They need a virtual network. They could write one from scratch. Or they could go to the module registry, see that the platform team has published a network module, read the documentation, understand what it provides, and use it. That moment, where they discover the standard instead of inventing their own, that's where governance stops being theoretical and becomes practical. Versioning is where the rubber meets the road. Semantic versioning, major, minor, patch. If the platform team makes a breaking change to the network module, maybe they change how subnets are named or alter the output structure, that's a major version bump. Version 2.0, everyone consuming version 1.0 keeps working. They're not forced to update. When they're ready, they plan the upgrade, they test it, they move to 2.0 on their schedule. The alternative is chaos. You publish a new version of a module. Suddenly 10 teams have breaking code. Pipelines fail. Production fails. People stay awake at 2 a.m. debugging why their infrastructure won't deploy. That's not governance. That's sabotage. Semantic versioning prevents this. Consumers pin to specific versions. They control when they upgrade. Breaking changes require planning. Access control around the registry is governance itself. Who can publish modules to ACR? Not everyone. This isn't gatekeeping, it's accountability. If anyone can publish, the registry becomes polluted. People publish incomplete modules. Modules with security holes. Modules that conflict with organizational standards. You need a publication process. Someone reviews the module before it's published. Does it follow naming conventions? Does it include documentation? Does it pass security scanning? Does it align with organizational constraints? The review isn't bureaucracy, it's quality control. It's the moment someone says, this module represents how our organization does infrastructure. That's not something you delegate to whoever feels like publishing. The registry becomes the source of truth for a single question. How do we do infrastructure in this organization? Not how the security team thinks we should. Not how the platform team hopes we will. How we actually do. The answer lives in the modules published to that registry, the versions, the documentation, the decisions encoded in parameters and variables. Module deprecation is a process that most organizations skip and then regret. Old modules accumulate. Version 1.0 of a pattern that got replaced by version 3.0 3 years ago still sits in the registry. Teams don't know if they should use it. The platform team doesn't know if anyone's still depending on it. When they finally decide to remove it, they break someone's pipeline. Proper deprecation works differently. You mark a module as deprecated in the registry. The documentation makes clear what the replacement is. You give teams a window to migrate, 6 months, a year, whatever makes sense. Then you remove the old version. Everyone's had time. Everyone knows the path forward. Deprecation is part of the lifecycle discipline. The registry isn't just where modules live, it's where governance becomes visible and operational. Landing zones, the architectural blueprint. Everything we've covered up to this point, modules, policies, scopes, lifecycle management, converges in a single place. The landing zone. This is where theory becomes the environment that teams actually work in. A landing zone is a pre-configured Azure subscription, not a resource group, not a collection of resources floating somewhere, a complete subscription that's ready for workloads to run. Someone from an application team comes to you and says, we need cloud infrastructure. You hand them a landing zone. They don't get an empty subscription with a task list of things they need to configure. They get a subscription where everything's already there. Here's what already there actually means. Network isolation. They've got a virtual network with the correct subnets for their application tier structure. They've got network security groups already configured with baseline rules. They've got route tables if they need to integrate with on-premises. They're not starting with blank networking. They're starting with a foundation that matches organizational standards. Identity integration works the same way. Entra ID is already connected. The subscription is discoverable within the organization's directory. Users have the right permissions to deploy resources. Application identities can authenticate without anyone manually wiring credentials. Service principals are pre-configured if the application needs them. Identity isn't a puzzle the team solves. It's a solved problem they inherit. Policy baseline is already applied. The policies you've defined at the management group level are already active. But more than that, there might be subscription-level policies applied specifically to this landing zone. If it's a production zone, stricter enforcement. If it's a sandbox zone, more permissive rules. The landing zone comes with the right policy posture built in. Monitoring is wired. Log analytics workspace is already there. Diagnostic settings are already configured so that anything created gets automatically logged. If something breaks, you've got the data to understand why. Monitoring isn't something the team configures after they've been running for 6 months and things go wrong. It's there from day one. The distinction matters between two types. Platform landing zones are shared infrastructure. This is where the hub network lives if you're doing hub and spoke. This is where shared services run. Directory services, DNS, backup systems. These are the subscriptions the platform team runs. Application teams don't touch them. They just consume the services and the connectivity. Application landing zones are workload specific. This is where the actual application infrastructure lives. The databases, the compute, the storage for user data. Each application team gets their landing zone. It's isolated from other teams, but it's integrated with the shared platform services. Network connectivity flows through the hub. Logs flow to the central log analytics. Identity flows through the organizational directory. Bicep is how you define all of this. A landing zone template isn't a single Bicep file. It's a composition of modules. The network module, the policy module, the monitoring module, the identity integration module, all orchestrated at subscription scope. You write a landing zone template that says, create a subscription with these characteristics, create its networking, assign its policies, wire its monitoring, integrate its identity. Here's where the architectural question surfaces. Are you building one landing zone, a static subscription you hand to a specific team, or are you building a template that can be instantiated many times? The answer determines your entire approach. If it's static, you can hard code decisions. If it's a template, every decision needs to be parameterized. What's the naming convention? What network range does this landing zone use? How does it connect to the hub? What policy baseline applies? What monitoring retention? These become parameters in your landing zone template. Azure Landing Zones, the ALZ reference architecture from Microsoft, provides the blueprint. It's not a template you use unchanged. It's a reference. It shows you what a well-designed landing zone looks like, what components are essential, how they fit together, what security principles guide the design. You take that reference and customize it for your organization. Your naming standards, your network architecture, your policy model, your identity integration patterns. The landing zone becomes the artifact where all your architectural decisions become real infrastructure. It's not a theory, it's not a diagram, it's a subscription that teams actually work in. Every team that gets a landing zone gets the same governance model, the same standards, the same controls. That's not limiting, that's consistency. That's the moment your architecture stops being aspirational and starts being operational. Multi-environment deployments, dev, test, prod. Here's the moment where theory meets operational reality. You've built modules, you've got them published, you've got a landing zone template that orchestrates everything. Now you need to deploy it 3 times, once for development, once for testing, once for production. And you need to do this without maintaining 3 separate Bicep files. The principle is straightforward. The same template works across all 3 environments. The difference is parameters. You write one main Bicep file. This defines your infrastructure architecture, what modules get composed, how they fit together, what the overall shape looks like. This main file has parameters, the decisions that need to be made. Then you create 3 parameter files. Biceparam files, one for dev, one for test, one for prod. Each parameter file answers the same questions differently. What location should this infrastructure run in? Dev might say US East, test might say US West. Prod might say both with failover configured. What SQ should the database be? Dev might be standard, test might be standard, prod might be premium. What's the backup frequency? Dev might have no backups. Test might have daily backups. Prod might have hourly. What network range? Dev might use 10.0.0.16, test might use 10.1 or 0.016, prod might use 10.2 and 0.016 and 10.3 and 0.016 for redundancy. The Bicep file is where you make decisions about how infrastructure should be structured. The parameter files are where you make decisions about what level of that structure you're willing to pay for and support in each environment. Here's the discipline this requires. Your Bicep variables should encode defaults. These defaults should reflect your baseline assumptions. The minimum security posture, the minimum monitoring, the minimum resilience that you require everywhere. Then parameters override those defaults for specific environments. If the environment is production, the parameter file says upgrade the SKU. Enable additional monitoring, configure failover. If the environment is development, the parameter file might say, use the cheapest option available that still meets compliance requirements. The governance question surfaces immediately. What's actually different between environments? This seems obvious until you're standing in an organization that has 3 copies of the same infrastructure that diverged 5 years ago, and nobody remembers why. Dev has a feature enabled that test doesn't. Prod is missing security controls that dev has. They're supposed to be the same architecture at different scales. Instead, they're 3 different systems that happen to run the same application. Clear thinking about this prevents the divergence. In most mature organizations, the differences cluster around a few dimensions. Access control is different. Dev might allow anyone with a subscription contributor role to deploy. Prod should require manual approvals. Who gets access to prod databases? Nobody on the dev team without explicit authorization. These access differences need to be reflected in parameters. Role assignments, RBAC constraints, Entra ID group memberships. Monitoring verbosity is different. Dev might log minimally, just errors and critical warnings. Test might log more. Information level, warnings, errors. Prod might log everything, including diagnostic data for performance analysis. These translate into parameter decisions about logging levels, retention periods, and alert thresholds. Cost constraints are different. You can experiment with expensive features in dev. Scaling isn't usually necessary. In prod, you want efficiency. This means sizing decisions, database SKUs, compute instance counts, whether you're using reserved capacity or on demand. Resilience requirements diverge. Dev doesn't need failover. Test might need failover between regions to validate it works. Prod probably needs it. This affects how many resources you deploy and how they're configured. The CI/CD pipeline validates each environment separately. A deployment to production triggers a different flow than a deployment to dev. Production requires approvals. Prod does policy validation. Prod might require the template to pass additional security scanning. Dev might just need validation that the syntax is correct. The payoff is enormous. You maintain one infrastructure architecture. You deploy it predictably to 3 different environments. Changes flow through consistently, and each environment gets exactly the level of resources and controls appropriate to its risk profile. That's not duplicate maintenance. That's architectural discipline. CI/CD integration, infrastructure as a delivery pipeline. You've got Bicep files sitting in Git. You've got modules published to a registry. You've got landing zone templates that define what infrastructure should look like. Now comes the part that turns all of this from intent into reality, the pipeline. The pipeline is where code becomes infrastructure. But more than that, it's where organizational discipline becomes automated enforcement. Think about what needs to happen between someone writes a Bicep file and infrastructure actually exists in Azure. The file needs to be validated. Does it compile? Are there syntax errors? Do the parameter names match the variable definitions? This catches obvious mistakes before they get deployed. Then it needs to be built. Bicep files get compiled into ARM templates. That's the format Azure Resource Manager actually understands. The build step produces artifacts, the ARM template, parameter files, documentation, everything needed for deployment. Next comes testing. You don't deploy to production without running the template somewhere first. Test deployments verify that the template actually works in an Azure environment. It will actually create the resources it claims to create. The outputs will actually produce what's expected. Policies will actually pass. This all happens in a non-production subscription where mistakes don't matter. Only after all of that comes actual deployment, and deployment itself has gates. Policy compliance checks validate that what you're about to deploy aligns with organizational standards. Security scanning looks for misconfigurations or security holes. In non-production environments, these gates might be automated. If it passes, it deploys immediately. In production, there's an approval gate. A human reviews what's about to happen. They see the proposed changes. They understand the blast radius. They either approve or reject. This enforces something crucial. Code is truth, but humans still decide. The pipeline stages themselves create the gates. Validate stage runs. If it fails, nothing moves forward. Build stage runs, test stage runs, deploy to non-prod stage runs, deploy to prod stage only runs if a human approves. This progression ensures that mistakes don't cascade. A syntax error gets caught in validation. It doesn't reach production. A policy violation gets caught in testing. It doesn't break production compliance. Authentication to Azure happens through the pipeline service connection. This is where credentials matter operationally. The pipeline needs to authenticate to Azure to actually deploy resources. Traditionally, this meant storing credentials somewhere, a service principal's password, a client secret. That introduces operational complexity. Where do you store it? How do you rotate it? What happens if someone gets access to it? Modern approaches use workload identity federation instead. The pipeline runner, the compute identity of the CI/CD system itself, is trusted by Azure through federated credential configuration. The runner doesn't need to store credentials. It just authenticates as itself. Azure trusts it. This eliminates an entire category of operational secrets. Idempotence is a principle that seems obvious and gets violated constantly. Run the pipeline twice. You should get the same result both times. The second run should update existing resources or do nothing if nothing changed. It shouldn't create duplicates. It shouldn't revert changes from the first run. This matters because pipelines fail sometimes. Networks hiccup, timeouts happen. You rerun the pipeline. If it's not idempotent, the rerun might create a mess instead of cleaning up the first attempt. The pipeline stages also define approval workflows. Who can approve deployments to production? In a small organization, maybe anyone with platform team membership. In a large organization, maybe only the platform lead or a designated rotation of people. In a regulated organization, maybe 2 people have to approve together. The pipeline enforces this. The gate won't open until the right approvals are in place. This prevents unilateral production changes. It's not human reviewers slowing things down. It's human reviewers making sure someone is accountable. The typical flow is validate, build, test, deploy, each stage validating and gating the next. Validation catches errors. Build creates artifacts. Testing verifies behavior. Deployment applies changes. Each step removes uncertainty. By the time resources actually get created in production, the organization has already verified every aspect of them multiple times. Mistakes haven't been eliminated. Humans still make mistakes, but the process catches the ones that can be caught automatically. This is where infrastructure code stops being a file sitting in Git and becomes a disciplined, repeatable, auditable process. Security by design, shift-left governance. The pipeline you've built validates and gates deployment. But those gates aren't just about catching syntax errors or preventing accidental overwrites. They're about embedding security into the infrastructure definition itself. This is shift-left security. The idea that you catch problems as early as possible when the code is written, not when it's running. Think about what happens in most organizations. Infrastructure gets deployed, it runs for a week, then security scanning happens. Someone realizes there's a hard-coded password in a configuration file. A storage account got created without encryption. A role assignment is too broad. Now you have to go back, fix it, redeploy it, and hope it doesn't break anything in production. This is backwards. Security shouldn't be something you discover after things are running. Shift-left flips this. Before a single resource gets created, before the template even compiles, you're running checks. Linting rules, scan the Bicep code and catch common mistakes. Hard-coded secrets. Missing tags when your organization requires tags on everything. Overly permissive access controls. Resource names that don't follow your naming convention. These rules catch problems at the source. Someone writes a line of code. The linter flags it immediately. They fix it before it ever gets committed to Git. Policy compliance checks happen next. Your organization has policies defined in Azure policy. Before you deploy to production, you want to know, would this template pass those policies? What if deployments actually instantiate the template in a test environment and run it through your policy engine? If the template creates a storage account without encryption, the policy flags it. If it tries to open ports that your organization forbids, the policy flags it. You find out before production, not after. The cycle time for fixing is minutes, not hours or days. This all happens in the pipeline, long before human approval. Automated checks create the first line of defense. By the time someone is reviewing a deployment for approval, they're not reviewing a blind template. They're reviewing something that's already passed multiple automated checks. The approval becomes a gate for judgment calls, not a safety net for obvious mistakes. Secrets management is where shift-left security becomes operational discipline. Bicep files go into Git. Git repositories are readable by team members who need to review code, but secrets can't live in Git. Never. Not in parameter files, not in Bicep variables, not anywhere. Linting catches hard-coded secrets immediately. If someone tries to paste a password into a Bicep file, the linter flags it. It won't let the file even compile. This forces the conversation. How do secrets actually get into production? The answer is Key Vault or pipeline secret stores. The pipeline injects secrets at deployment time. The Bicep file doesn't know what the password is. It just knows there's a secret it needs. The pipeline retrieves the secret from Key Vault during deployment and passes it in. The secret never sits in code. It never gets checked into Git. It never lives anywhere it shouldn't. Managed identities represent the modern approach to this problem. If a resource needs to authenticate to another service, it doesn't need a password. It can use its managed identity. Azure issues it a credential automatically. There's nothing to store, nothing to rotate, nothing to leak. This is simpler and more secure than the alternative. Auditability is the final piece. Every deployment should leave a trace. Who deployed what, when, and why should be recoverable. Git history shows what changed. Pipeline logs show what ran and what the output was. Azure audit logs show what resources were created and by which identity. If something goes wrong, you can trace back through all of these layers and understand exactly what happened and who did it. Security being embedded in every stage means it's not a separate concern. It's not something bolt-on, it's architectural. From the moment code is written until resources are running in production, security is being checked continuously. Problems get caught early, secrets stay protected, access stays controlled, auditability is automatic. That's shift-left security. That's where architecture meets operational reality. Bicep versus Terraform. The strategic choice. At some point, someone on your architecture team will ask the question, should we be using Bicep or Terraform? The question usually carries weight, like you're supposed to declare a winner. Pick a side, commit. The reality is messier and more interesting than that. Both are valid approaches. The choice depends entirely on what you're building, not on which tool is technically superior. This matters because it's a foundational decision. It shapes how your team thinks, how your pipelines are structured, how your modules are organized, what you'll struggle with and what you'll take for granted. Bicep is Azure native. It moves at the speed of Azure itself. When Microsoft releases a new service, Copilot in your infrastructure, new compliance controls, novel security features, Bicep supports it immediately. Not eventually, not in the next provider update cycle. Immediately. The language compiles directly to ARM templates. There's no translation layer, no abstraction that might lag behind Azure's evolution. This is enormously valuable if your organization is primarily on Azure and you need to stay current with whatever Microsoft ships. There's no separate state file. This sounds like a limitation until you experience the operational weight of managing state files. Terraform maintains an explicit state file that tracks what it's managing. This state file is truth. It tells Terraform what resources exist, what properties they have, what the current versus desired state looks like. This is powerful. It enables detailed planning and drift detection. It's also operationally complex. Where does the state file live? Who has access to it? How do you back it up? What happens if it gets corrupted? What happens if two people deploy simultaneously and the state file gets into an inconsistent state? Bicep sidesteps all of this. Azure Resource Manager is the source of truth. You deploy a template. ARM applies the changes. The actual resource state in Azure is what matters. Terraform is multi-cloud. This changes everything if you're managing infrastructure across AWS, GCP, Azure, and on-premises simultaneously. With Terraform, you write one workflow that spans all your clouds. One CI/CD model, one language, one way of thinking about infrastructure. The Terraform registry contains modules for virtually every platform and service. AWS modules, GCP modules, Kubernetes modules, Datadog modules. If it has an API, someone's written a Terraform module for it. This is the lingua franca of infrastructure teams managing anything beyond a single cloud. The trade-off is that Azure-specific features sometimes arrive later in Terraform than in Bicep. The Azure provider needs to be updated by the maintainers. It happens quickly, usually days, not months, but there's still a lag. For cutting-edge Azure features, Bicep gets there first. State management in Terraform is both a strength and an operational burden. The state file enables powerful drift detection. Terraform can compare what it expects versus what actually exists in Azure and tell you exactly what changed. It can target specific resources for updates. It can perform sophisticated dependency ordering. These capabilities come from that state file, but they come with the requirement that you manage it carefully. Production state files need to be protected, encrypted, backed up, and audited. This isn't something you bolt on casually. It's a design decision that ripples through your infrastructure practices. Here's where Azure Verified modules matter to this conversation. AVM exists in both Bicep and Terraform. It's the same architectural thinking, implemented in both languages. This means your organizational standards don't have to choose a language. You can standardize on architectural principles, how networks should be configured, how identity should integrate, what compliance baselines should look like, and then implement those in whatever language your team prefers. The decision ultimately comes down to scope. Are you building Azure infrastructure? Is Azure your cloud? Then Bicep is probably the right choice. It's native, it's current, it's simpler operationally. Are you managing multiple clouds? Is Azure one piece of a larger infrastructure puzzle? Then Terraform is probably right. You get a single tool, a single workflow, a single way of thinking that spans your entire infrastructure estate. The architectural principles we've covered, modules, governance, scopes, lifecycle management, all apply to both. The differences are in implementation details. The outcome should be the same. Infrastructure that's governed, reproducible, auditable, and manageable at scale. Pick based on your actual situation, not based on which tool sounds better in a conversation. Governance at scale. Multiple teams, multiple stacks. The architecture we've built so far works beautifully in theory. One landing zone template, one set of modules, one governance model. But theory meets reality when you're not deploying infrastructure for a single workload. You're deploying for dozens of teams, hundreds of subscriptions, thousands of resources spread across environments that barely communicate with each other. Governance doesn't collapse just because scale increases. It has to evolve. Enterprise environments force a different question. Not how do we govern our infrastructure, but how do we govern while letting teams move independently? The answer is boundaries. The clearest boundary is ownership. A platform team exists. Their job is building the foundation. They own the management group hierarchy. They own the shared infrastructure, the hub network, the directory integration, the central logging. They own the policies that apply across the entire organization. They publish modules. They maintain the module registry. They set standards. Application teams exist separately. Their job is building products. They own specific subscriptions. They own the resources their application needs. They don't own the shared layer. They consume it. This separation prevents two things from happening simultaneously. Application teams can't break shared infrastructure by accident. They can't modify the networking layer and accidentally cut off connectivity for everyone. They can't change RBAC in a way that locks out the security team, but also the platform team doesn't become a bottleneck. Application teams have autonomy within their own subscription boundaries. They can deploy resources, they can configure their application, they can iterate quickly. The multiple stacks pattern reinforces this boundary. The platform team manages several stacks, one for connectivity, the hub network, the routing, the integration with on-premises or cloud providers. One for identity, service principals, managed identities, role assignments at the tenant level. One for shared services, log aggregation, backup infrastructure, disaster recovery. Each stack has its own lifecycle, each has its own approval process, each is versioned separately. Application teams deploy their own stacks within the subscriptions they've been allocated. Their stack creates the resources specific to their application. Virtual machines, databases, storage, APIs, but these stacks operate within the governance boundaries set by the platform stacks. The networking stack has already created the virtual networks and subnets. The application stack deploys into those networks. The identity stack has already configured role assignments. The application stack uses those identities. The application team isn't reinventing the wheel. They're working within a framework. Deny settings on platform stacks enforce this boundary technically. The platform team sets deny write and delete on the networking stack. Application teams can read the network configuration. They can deploy into the networks, but they can't modify the networks themselves. They can't change routes. They can't alter security groups in ways that would affect other applications. The deny setting makes the boundary hard. It's not a suggestion. It's a technical control. The governance model needs to be explicit. Teams need a document, or better, a living reference in your documentation system that answers three questions. What's shared? The hub network, the directory, the log storage, the backup infrastructure. Teams know this is owned by the platform team. Changes require platform team approval. What's delegated? Application teams control their subscriptions. They can create resources. They can modify application-specific configuration. They can iterate what's forbidden, certain resource types, certain configurations, things that would violate policy or compliance. Teams know these are off limits. The policies prevent them. The documentation explains why. This model scales because it's self-explanatory. New teams onboard into a landing zone. They read the documentation. They understand the boundaries. They understand what they own and what they don't. They understand what they can do and what requires escalation. The platform team doesn't need to brief every team individually. The model is codified. It's reproducible. It's in the infrastructure itself. Governance at enterprise scale works because it's not trying to control everything. It's controlling what matters and delegating the rest. Drift, compliance, and continuous validation. You've got your infrastructure defined in Bicep. You've got it deployed through a pipeline. You've got governance enforced at multiple levels. And then reality happens. Someone logs into the portal at 2 a.m. on a Sunday to troubleshoot a performance issue. They make a change. Just a quick SKU upgrade on a database. They plan to document it on Monday. They never get around to it. Now your template says one thing, your actual infrastructure says another. That gap is drift. And if you're not watching for it, you'll never know it's there. Drift is the quiet failure mode of infrastructure as code. The template isn't wrong. The infrastructure isn't broken, but they're no longer synchronized. Over time, drift compounds. One change becomes two becomes five. Eventually, your infrastructure has evolved so far from your template that nobody's quite sure what the actual topology looks like. Deploying again becomes risky. You might overwrite changes you didn't know about. You might break something. Deployment stacks address part of this. A stack tracks which resources it manages. When you run a deployment, the stack knows exactly which resources are supposed to be there. If a resource has been manually deleted, the stack detects it. If a resource has been manually created that wasn't in the template, the stack sees it's unmanaged. But here's the limitation. The stack can't automatically decide what to do about unmanaged resources. It can track them. It can report them. It can't fix them without explicit configuration. Azure policy is the complementary piece. Policies define what compliant infrastructure looks like. A policy might say, all storage accounts must have encryption enabled. All networks must have network security groups. All applications must have monitoring configured. When you violate a policy, it doesn't prevent the action, unless you've set the effect to deny. But it does flag the resource as non-compliant. That flag appears in compliance reports. You know something's wrong. The discipline comes from continuous validation. What if deployments aren't just for before deployment previews? They're continuous monitoring tools. Run what if regularly. Every day. Every week. Compare what your template says should be there with what actually is. The difference is drift. When you see drift, you have a choice. Redeploy the template to bring reality back in line, or update the template to match reality. Either way, you're making a conscious decision. You're not allowing drift to accumulate silently. Compliance monitoring should be the same. Not a quarterly audit, not a security review once a year. Continuous. Dashboards that show policy compliance in real time. Which resources are compliant, which are flagged as non-compliant, which policies have exceptions, how many resources are managed versus unmanaged. These dashboards need to be visible, not hidden in a compliance portal that nobody checks. They should be in your operations center. On your team's dashboards, where people see them every day. The principle is straightforward but often violated. Infrastructure should match the template. When it doesn't, that's not normal operational variance. That's a problem. The problem might be that someone made a change they shouldn't have, and now you need to investigate and understand why. The problem might be that the template is out of date and needs updating. The problem might be that the policy is too strict and needs adjustment. Whatever the problem is, it needs attention. This is the difference between treating your infrastructure code as documentation and treating it as truth. Documentation describes what you think exists. Truth is what actually does. The infrastructure as code approach only works if you're committed to keeping them synchronized. That synchronization is continuous work. It's drift detection. It's compliance monitoring. It's validation running regularly. It's not something you do once and move on. Compliance isn't a checkpoint you pass. It's an ongoing practice. Migrations and brownfield scenarios. Most organizations don't start with Bicep. You inherit a reality. Someone deployed resources through the portal 3 years ago. Another team wrote ARM templates that nobody fully understands anymore. A third team uses Terraform. You've got Azure resource graph queries that reveal orphaned resources nobody remembers creating. You've got virtual networks configured through scripts that live on someone's laptop. You've got a brownfield. The question isn't how to build perfect infrastructure from scratch. It's how to gradually transform what exists into something governed and maintainable. The migration isn't a cutover. This is critical. You don't wake up one morning and decide everything converts to Bicep by Friday. That's how you break production. Migration is a journey. It happens incrementally. It happens in stages. Some workloads move first. Others follow on their own timeline. The typical pattern starts with new resources. Every new resource should be Bicep, not eventually, from now on. When a team wants to deploy something new, they define it in Bicep. They go through the governance process. They use the landing zone template. They integrate with the module registry. This decision alone, that new things are always Bicep, begins the transition. Over time, new resources accumulate. The Bicep portion of your infrastructure grows. Existing resources can be adopted into Bicep through export. Azure has a feature that lets you export the template for any existing resource. You export a virtual network that was created manually through the portal. You get an ARM template. That template becomes the basis for your network module. It's messy. The exported template includes every parameter, every property, most of which you don't actually care about. But it's a starting point. You refactor it. You strip out the noise. You parameterize the decisions. You add documentation. The exported template becomes your module. This adoption process works for individual resources or for entire resource groups. Export everything in a resource group. You get one large template that defines the whole group. Now you decide how to split it into modules. Maybe one module per resource type. Maybe one module per logical architecture layer. The refactoring is work, but it's work you can do safely. The resources already exist. You're not creating anything new. You're just creating a Bicep representation of what's already there. The governance question surfaces immediately. What's your migration strategy? Which workloads move first? This isn't academic. It has real consequences. Some teams will have dependencies on other teams' infrastructure. If you migrate a networking infrastructure first, but the application teams aren't ready to handle parameterized networks, you create friction. Better to think through the dependency graph. Identify what can safely move independently. Start there. Build momentum. Let success in one area create demand in another. Brownfield environments are fundamentally messy. You're not cleaning a blank slate. You're renovating a house someone's been living in. They've made modifications. Things connect in ways the original architects didn't intend. You'll find resources that are no longer in use, but nobody's deleted them. You'll find manual configurations that don't match any documentation. You'll find policies that contradict each other. Bicep should be the target state, but the actual state is going to require cleanup. The principle is straightforward, but often tested in practice. Every new resource should be Bicep. Not every important resource. Not every resource we have budget to migrate. Every resource. This means when developers want to deploy something, they write Bicep. When operators need to make changes, they modify Bicep. When new capabilities ship in Azure, teams who want them write Bicep to implement them. The investment shifts from managing existing messy infrastructure toward building Bicep definitions of new infrastructure. Gradually, and this takes time, measured in years, not months, the entire estate becomes code-driven. Old portal-created resources eventually get decommissioned and replaced with Bicep versions. Legacy ARM templates get refactored into modules. Manual configurations get captured as code. You don't finish the migration, you complete specific phases. Each phase leaves you in a better state than you started. More predictable, more governed, more maintainable. That's how you transform a brownfield into a controlled platform. The 2026 landscape, what's changing? The Azure platform doesn't stand still, and neither does the role Bicep plays in it. Looking at 2026, several shifts are happening simultaneously. They're not separate developments. They're pieces of a coherent movement toward infrastructure as the control plane of the organization. Azure Blueprints officially disappeared. July 2026. This isn't a surprise that's coming. It's already here. Blueprints were Microsoft's first attempt at solving the "how do we govern at scale" problem. They bundled templates with policies and role assignments. They could assign those bundles to management groups, but they hit a ceiling. They weren't versioned like modern software is. They weren't integrated with CI/CD. They were difficult to maintain. Deployment stacks replaced them. Stacks are native Azure resources. They're versioned, they integrate with everything else, they have state awareness, they work seamlessly in pipelines. The migration from blueprints to stacks matters because it signals that governance infrastructure is now treated like application infrastructure. Deployment stacks themselves are getting richer. The deny settings we've talked about, those hard protections against unintended modification, are becoming the standard governance pattern. Deny settings prevent certain actions on stack-managed resources. This shifts how people think about access control. You don't just ask who can deploy. You ask what they can modify once it's deployed. Lifecycle controls around deletion and detachment are becoming more sophisticated. Organizations can now configure stacks differently in different environments. Aggressive cleanup in dev, conservative protection in prod, all expressed as configuration, not as separate processes. Entra ID resources now have general availability Bicep support. This is significant because it completes the picture. Identity used to be something you configured separately. You'd deploy infrastructure in Bicep. Then separately, you'd set up identity integration. It was fragmented. Now identity is part of the infrastructure definition. You define service principals in Bicep. Managed identities, conditional access policies, role assignments, all in the same code base as everything else. Identity as code isn't theoretical anymore. It's operational. Azure verified modules continue expanding. More resources, more patterns, more standardization. Where once AVM was a curated collection, it's becoming the expected baseline. New resources in Azure ship with corresponding AVM modules. Not eventually, not next quarter, alongside the resource itself. This accelerates the adoption of standards. Teams don't have to decide how to configure something novel. AVM already has a recommended approach. It's tested, it's documented, it's versioned. The ecosystem is converging in an important way. Bicep and Terraform AVM modules follow the same specifications, the same parameter patterns, the same outputs, the same documentation structure. This convergence means architectural standards become tool independent. You can standardize on how networks should work, how identity should integrate, how compliance should be enforced, and then teams can implement those standards in Bicep or Terraform depending on their context. The standards aren't locked to a language. Infrastructure code is becoming the control plane, not the mechanism for deploying things, the mechanism for governing them, for controlling them, for ensuring they don't drift, for assigning ownership, for tracking lifecycle. Bicep is the vehicle, but the concept extends beyond it. The platform itself, the management groups, the policies, the deployment stacks, the role assignments, all of it is now defined in code. This is the transition from infrastructure as code, as a deployment convenience, to infrastructure as code as organizational governance. Organizations adopting this model now have a significant competitive advantage, not in speed, though they'll be faster, but in predictability, in compliance, in the ability to adapt when business needs change. When a merger happens and you suddenly need to integrate another organization's Azure footprint, you don't negotiate how you'll govern it. You don't manually configure it. You have a template, you instantiate it. You've already codified how governance works. It's not a project, it's a deployment. The organizations that haven't adopted this model by 2026 are increasingly at a disadvantage. They're still managing infrastructure through change management conversations, through ticket systems, through manual approvals. They're hoping configurations stay consistent. Bicep and the practices around it eliminate that guesswork. Bicep isn't syntax, it's the architecture of organizational governance expressed in code. The separation between hobby projects and enterprise is lifecycle awareness, contract enforcement, and state visibility. Deployment stacks, Azure verified modules, and management group scopes aren't features. They're evidence of this shift. They're proof that infrastructure code has become the control plane. Start with modules, publish them, enforce their use. Your entire infrastructure becomes a reflection of your organizational principles, not an afterthought to your business operations.